Okay, now let's talk about matrix inverses. I've alluded to these in the past couple of lectures, and they've played an important role in the background of what I've been talking about, and now we're going to bring them to the foreground. So, I think many of you know the identity matrix is the matrix with ones down the diagonal. And this is almost always written I for identity, and sometimes I'll write I sub n if it's an n by n matrix where the n indicates the size. And the nice thing about the identity matrix is if you take the identity matrix and you multiply it by any other matrix, you just get that matrix back again. The identity matrix is like the number 1. And it also works on the other side. A is equal to A times I. So if you multiply on the right or the left, it gives you back the original matrix, and that's very easy to see. And the definition, if A is an n by n matrix, and I should say here that all of my matrices I'm talking about are going to be square matrices, let's say size n by n. If A is an n by n matrix, A inverse is a new n by n matrix, and it's defined to be the matrix with the property A inverse times A is equal to the identity. So that's the defining property of the inverse. A couple of comments are in order here. So it's not entirely obvious that there's only one such matrix. How do you know there aren't several matrices which satisfy this? It's also not clear that there's any matrix which satisfies this, and in fact there isn't always. And another subtle point is that the matrix also satisfies the property that A inverse is equal to 1. So here I have the A inverse first, and here I have the A inverse second. The inverse works in either order. Okay, so let's do a couple of really simple examples. Let's take a little diagonal 2 by 2 matrix. If A is the matrix with 3 forward down the diagonal, then A inverse is the matrix what? Well, if you think about it, it's just 1/3, 1/4 down the diagonal, because if you multiply these two matrices, you get the identity. In general, diagonal matrices are very easy. If A is A1 down to AN, then A inverse is just the inverses, A1 inverse, down to AN inverse. Okay. Here's another simple example. If A is the anti-diagonal matrix with 1s on the diagonal, then interestingly enough, A inverse is what? Just itself. Because if you multiply this matrix times itself, indeed you get the identity. A sort of obvious non-example is if A is equal to the 0 matrix, then there's no way you can multiply that by anything to get the identity, so A inverse does not exist. EXIST. All right, let's see. Let's compute the inverse of this matrix, 1, 2, 1, 3. How do you find the inverse of this matrix? You're looking for another matrix such that when you multiply them, you get the identity. Well, you poke around, I don't know. Here's the answer, 3, 1, minus 2, minus 1. In general, there's a nice formula for the inverse of a 2 by 2 matrix. A, B, C, D inverse is equal to 1 over AD minus BC times DA minus B minus C. And that, if you think about it, certainly requires that AD minus BC is not equal to 0 for this to make any sense at all. And in fact, a 2 by 2 matrix has an inverse if and only if AD minus BC is not 0. And there's its formula. And I'm sure many of you recognize that as the determinants. I suggest that you work this formula out for yourself, at least check the formula that's written down here. And if you want to see how that's derived, it's on page 32 in the book. Okay, now we're going to do an important class of examples. Let's suppose that E is an elementary matrix. So let's just do a very simple 2 by 2 example. Basic elementary matrix is this one, and just sort of obviously, or by the formula above, its inverse is this matrix. So that is to say, if this is E, then E inverse is you just take the same matrix and change the 2 to a minus 2. And in general, that's how you compute the inverse of an elementary matrix. An elementary matrix has a single number k somewhere, and the inverse of that matrix is the same matrix, except you change that k to a minus k. Okay, now a very important property of inverses is what happens with products. So suppose I have 2 matrices A and B, and again everything's n by n, and suppose I know A inverse and I know B inverse. Suppose I've computed those already, and then I take the matrix C, which is A times B. The question is, what is C inverse? So I'll let you think about that for a moment. Actually, why don't you pause the presentation here if you don't know the answer already, and think about that for a moment and see if you can come up with the answer. Okay, well, let's see. Maybe the most obvious guess is that C inverse is simply A inverse times B inverse. But if you think about it, I don't know, let's see. Let's see if that's true. Well, let's multiply C times C inverse, our proposed C inverse, and see if we get the identity. Well, C is A times B, and then you multiply that times A inverse, and multiply that times B inverse, and if I have the right formula, that had better give me the identity. Well, the problem is that this B here is stuck in the middle between the two A's. I'd like to cancel these. Have these give me the identity and these give me the identity, but matrix multiplication is not commutative. This is not necessarily equal to A times A inverse times B inverse. If matrix multiplication was commutative, I could switch these two to this order, and then I would have the identity, because this is the identity times the identity. But there's a big no here. Matrix multiplication is not commutative. So what do you do? Well, I think many of you know probably the answer is to switch the order. So this is an important fact. oops, let's make it in black, is an important fact. If you take a matrix A and a matrix B, and you want to compute the inverse of the product, it's B inverse times A inverse in the opposite order. And let's check why this is true. Well, what do I need to know? I'm claiming the inverse of this matrix is this matrix, so in order to check it, I have to check that if I take AB and multiply by its purported inverse, which I'm claiming is B inverse A inverse, I'm hoping that that's equal to the identity. Well, now things are in the right order. These two guys here give me the identity, and I get A times the identity times A inverse. And the identity times anything is the identity, is itself. So you get A times A inverse, and A times A inverse is indeed the identity. So, definition, we say A is invertible if it has an inverse. And from the fact above implies if you have a bunch of matrices A1 up to AN, which are invertible, so is the product. And in fact, the inverse is the inverse of the individual terms in the opposite order. But never mind the formula. An important point is simply that taking product of invertible matrices is invertible. Okay, an important special case of this, which we're going to be using repeatedly, is the following. Suppose L is special lower triangular. Then it's invertible. And in fact, it's fairly easy to compute the inverse. The reason this is true and the way you compute it is that you write L as a product of elementary matrices. And since elementary matrices are invertible, L inverse is simply En inverse times E1 inverse. And recall that each of these guys, each individual inverse of an elementary matrix is also an elementary matrix, where you recall you just take the matrix and change the sign of the only non-diagonal term. So the upshot is that it's very easy to compute inverses of lower triangular matrices, and it's convenient to do that, to take advantage of that often. Okay, now I'm going to explain an algorithm for computing matrix inverses called Gauss-Jordan Elimination. I'm going to illustrate this with a very simple example. Before we computed the inverse of this 2 by 2 matrix 1, 2, 1, 3. And how do we compute the inverse of this matrix? Well, the sort of brute force method would be to say, okay, I'm looking for a 2 by 2 matrix, and I don't know what matrix that is, so let's just call it X, Y, Z, and W. I'm trying to find X, Y, Z, and W, which make this true. That's exactly what the inverse is. So that's 4 equations in 4 unknowns. Now, how do you solve that? Well, this is basically something we've done. I'm going to simplify it a little bit, sort of condense it as follows. Concentrate on this column and this column over here. If you pull those out, what you're trying to solve is 1, 2, 1, 3 times xz is equal to 1, 0. And similarly, if you focus on the second column, you'd be trying to solve 1, 2, 1, 3 times yw is equal to 0, 1. Okay. Okay, well, either of these 2 equations are easy to solve. This one, for example, if you use the method of augmented matrices, you would write it as 1, 2, 1, 3, 1, 0. And I'm not going to put the closed parentheses in yet. And I would do row and column operations to this matrix to try and make this part upper triangular, for example. And if I did the same thing to this one, I'd get an augmented matrix where this part's still the same, and over here I'd have 1, 0. So it makes sense to combine them into a single 2 by 4 augmented matrix like this. And the idea of Gauss-Jordan elimination is that in order to solve for the inverse of this matrix, what we're going to do is row and column operations to this matrix. Okay, let's see how this works. So I've written down our 2 by 4 augmented matrix. And what we're going to do is perform row and column operations in such a way that reduce this matrix to the identity. And when you do that, this matrix over here will become the inverse. Okay, so let's see how that works. So you want to do row and column operations to this part of the matrix, which will make this the identity. So for example, you could add minus 1 times the first row to the second. And what does that do? Well, you don't touch the first row. And when you add minus 1 times this to this, you get 0. Minus 1 times this to this, you get 1. Minus 1 times this is minus 1, and 0. Excuse me, 1. Maybe that didn't look right. Okay, now we're going to continue. Now, this is an upper triangular matrix, so if you're really just doing linear systems like we've done before, you might stop here. We're going to go a little further. We're going to actually reduce this matrix to the identity. How do we do that? Well, the next step is what we do is we add minus 2 times the second row and add it to the first row. And what that gives you is what? Well, the second row is going to stay the same, so you're going to have 0, 1, minus 1, 1. And when you add minus 2 times this row to this row, it doesn't affect that. Minus 2 times this gives you a 0 here. Minus 2 times minus 1 is plus 2, and add that to 1 to give 3. And minus 2 added here gives you minus 2. And now, since this matrix is the identity, this matrix here is the inverse. and that is the inverse that we computed before. Let me illustrate this with a discussion of the LU decomposition. So suppose we had an equation of the form AX is equal to B. In some sense, I've given you two ways to solve this equation, which are intimately related. So the first is to find a special lower triangular matrix A such that LA is equal to U. And then you multiply both sides of this equation by L to get the equation LAX is equal to LB. And that gives you the equation UX is equal to LB. And since U is upper triangular, you can solve this by back substitution. Now, a very similar thing, but slightly different, is what I talked about finding the LU decomposition of A. Suppose I find the LU decomposition of A. And I'm going to give this another name. I'm going to call this L tilde U because it's a different L than before. Suppose I find a decomposition of A into a special lower triangular matrix times an upper triangular matrix. That's what we call the LU decomposition of A. So then if I did that and I was going back to solve my original equation, I would plug in LU for A, and I'd get L tilde U for A. And now what? What have I done? I've replaced A with this L tilde U. That's not, on the face of it, that useful. But now what you do is you multiply both sides of this equation by L tilde inverse. And what happens when you do that is L tilde inverse times L tilde gives you the identity, and you get the equation, let me use a bolder color here, you get the equation UX is equal to L tilde, I multiply both sides of this equation by L tilde inverse B. Okay. And now this is an upper triangular system, and it's very easy to solve. Okay, so the moral of the story is that these two methods really are the same. Writing LA is equal to U, or LU is equal to A, is essentially the same thing, and the way you get between these two is from here to here. You see that the relationship is L tilde is simply L inverse. And that's what I mean by it being convenient when you have invertible matrices. You can move them from one side of an equation to the other, and that's exactly what I've done here. If you take this equation, well, you move the L tilde to the other side to get a simpler equation, and the only cost is that you've had to replace this L tilde with L tilde inverse. And especially for special lower triangular matrices, it's quite easy to compute the inverse. So that's, in some sense, a cost-free operation, especially from the computer science point of view. So these two methods are really equivalent.